This video is a little overview of this titration problem in which we're going to calculate the pH at various points along a titration between butanoic acid and sodium hydroxide. I just want to show you and talk a little bit about how the pH changes as you add more and more sodium hydroxide. Let me write the reaction equation down here at the bottom that we will be looking at. The butanoic acid is going to react with the sodium hydroxide, and what it really reacts with is the OH of that sodium hydroxide. And the sodium hydroxide being strong forces this as a one-way reaction, is not in equilibrium, to produce the anion, COO minus, and water. And as more and more sodium hydroxide is added, the pH is rising, so we see this on the curve. We see a rise in it until we get to the equivalence point, and at the equivalence point we know that is when we have added equal number of moles of the butanoic acid and the sodium hydroxide. And then we can go past that and the pH will continue to rise as you add more and more sodium hydroxide. So A is the point in which we have added no sodium hydroxide. And at the equivalence point we're going to be at F, and let's talk about how I know that to be the equivalence point, F. I'll go ahead and write that down here. The reason I know this is because I have the concentration of butanoic acid and the concentration of sodium hydroxide as the same concentration. So if they have the same concentration and it's a 1-to-1 ratio, it's going to take the same volume. So we are here at 20 milliliters at the equivalence point of sodium hydroxide added. So halfway to that point would be 10 milliliters. So right here we're at question B, part B of this problem. 15 milliliters would be halfway between B and the equivalence point, so this is going to be part C at 15 milliliters. Then we start inching our way up to the equivalence point, and the pH starts changing pretty rapidly. At 19 milliliters, maybe this is part D at 19, and then we're even closer at part E, and then we shoot past it. We shoot rapidly past it, so at 20.5, it's just barely past. It's rising rapidly. So this is part G, and then it's rising really high at part H. Okay. Now the parts here where the rapid rise is occurring right near the equivalence point, very different pH than at the equivalence point, but very, very close in value to that equivalence point. So the way we work the problem is going to be a little bit different than what a typical titration problem will be when we work a problem for that. Now the other thing I want to talk about is this region right here. This region right here where the pH is rising but slowly is a buffer zone. Okay, it's a buffer region. And when we do calculations along this region, we'll be able to use the Henderson-Hasselbalch equation to solve for the pH. Let's talk about why this is a buffer. First of all, let's think about the definition of a buffer. A buffer is a solution that resists changes to pH when you add an acid or add a base. What are we adding? Well, let's get a picture in our mind of what's going on here. We have got our solution, okay, and in this flask is our acid, and I'm just going to label it HA, and I've got 20 milliliters of that acid in this flask, and we're monitoring the pH of this flask. Now we've got above this flask a burette that contains the sodium hydroxide. Get it drawn here in my ugly way, but that's got the sodium hydroxide in it. So we are adding sodium hydroxide to this solution. At first it changes kind of rapidly. It's not a buffer region, and then it levels off. If you add a base to a solution and it resists change to pH, that is the definition of a buffer. So we see it in action. But we also can see the ingredients present here. We have in our flask at these points B and C butanoic acid. We've added sodium hydroxide. It has converted some of the butanoic acid over to its conjugate base. So a solution which contains a significant amount of a weak acid and its conjugate base, that is the parts of a buffer. So we know we're in a buffer region both by the definition of resisting change to pH, seeing that it's leveling off, and seeing it as a buffer in that it contains some of both substance. Okay, so this is the overview, and then you can go and watch each of the parts, A through H, of how to determine the pH along this